Rock doesn't break the way most people think it breaks. Most people think rock breaks with force. Hit it hard enough with a big enough machine, and it shatters. That's how the drill rigs work. That's how the excavators work. That's how a $200,000 hydraulic rock drill works. It pushes a carbide bit into the rock face with 40,000 pounds of downward force and grinds through by brute pressure and rotational speed. And it works on most rock, on sandstone, on shale, on soft limestone, on anything that yields to pressure the way a cracker yields to a thumb. The drill pushes, the rock crumbles, the bit advances 3 feet per hour through soft material, 1 foot per hour through medium. The drill rig is a machine designed to push through resistance, and on most days, the resistance loses. But there's a rock that the drill doesn't push through. Not because the rock is harder than the bit. The carbide bit is harder than any natural rock, because the rock is tougher. And hardness and toughness are not the same thing. On a Tuesday morning in October of 2001, a drilling contractor named Gary Hoskins positioned his $200,000 Atlas Copco hydraulic drill rig on a hillside in Carter County, Kentucky, aimed the bit at a ledge of Berea sandstone, and started drilling a channel for a new county road culvert. The job was straightforward: cut a trench through 8 feet of rock, lay the culvert pipe, backfill, pave. 3-day job, $18,000 contract. The kind of work Gary's rig did 3 times a month across eastern Kentucky. The bit hit the Berea sandstone and stopped making progress. Not stopped, as in the engine stalled. The engine ran fine. The hydraulic pressure was at full spec. The bit was turning. The carbide teeth were engaging the rock face, but the rock wasn't moving. The bit was grinding against the surface, creating heat and dust and noise and no penetration. The sandstone was absorbing the force of a 40,000-pound drill and giving back nothing. Gary checked his equipment. Bit condition, good, recently resharpened. Hydraulic pressure, 3,800 pounds per square inch, within spec. Rotation speed, 120 revolutions per minute, standard. Water flush, running, clearing the cuttings. Everything was right. The machine was performing exactly as designed. The rock was simply refusing to yield. He drilled for 4 hours, in 4 hours of continuous operation, 4 hours of full hydraulic pressure, full rotation, full water flush. The bit advanced 11 inches in 4 hours. At that rate, the 8-foot channel would take approximately 35 hours of drilling time, 4 to 5 days, instead of the estimated 1 day. The $18,000 contract would cost Gary $12,000 in fuel, wear, and labor before he was halfway through. He called the county road supervisor, a man named Dale Shepard. "Dale, I've got a problem. The Berea at this site is different from what I've drilled before. I'm getting 11 inches in 4 hours. I can't get through this rock with my rig. Not at any speed that makes the contract workable." "What do you mean you can't get through it? It's sandstone. You've drilled sandstone 100 times. This isn't normal sandstone. I don't know how to describe it. The bit engages, but the rock flexes instead of fracturing. It bends under the pressure and springs back when the bit passes. I've never seen sandstone do this." Stay with me, because what happened next and how it changed everything about this 3-day road job is why this story is still told in Carter County. Let me tell you about the rock, because what Gary was drilling into wasn't ordinary Berea sandstone. It was a specific formation within the Berea, a silica-cemented layer that geologists call the iron band. Not because it contains iron, because it's as hard to cut as iron. The Berea sandstone in eastern Kentucky is generally a medium-hard sedimentary rock. Compressive strength of about 8,000 to 12,000 pounds per square inch, well within the range of a hydraulic drill. But at certain horizons within the Berea, the sand grains are cemented together with secondary silica instead of the typical calcite or clay matrix. Silica cement creates a bond between sand grains that is nearly as strong as the grains themselves, essentially turning the sandstone into a solid block of quartz. The silica-cemented Berea has a compressive strength of 25,000 to 30,000 pounds per square inch, 2 to 3 times harder than normal Berea. And more importantly, it has a property that hardness alone doesn't describe. It's tough. It absorbs energy without fracturing. A hard but brittle rock, like granite, will shatter when you hit it right because it can't flex. A tough rock, like silica-cemented sandstone, absorbs the impact, distributes the stress through its matrix, and returns to its original shape. The drill bit pushes, the rock flexes microscopically. The bit passes, the rock springs back. Progress is measured in fractions of an inch per hour. Gary's $200,000 drill rig was designed for hard, brittle rock. It generated massive downward force and relied on the rock fracturing under that force, but the iron band didn't fracture. It flexed, and no amount of additional force would change that, because the failure mode of silica-cemented sandstone isn't fracture, it's abrasion. You can grind through it, millimeter by millimeter, but you can't break through it. The drill bit was essentially trying to punch through a boxing glove. The harder you hit, the more it absorbs. If you're enjoying this story, consider subscribing to The Average Farmer. We share stories like this every week. Let me tell you about Emmett Boggs, because Emmett was standing at the fence above the road cut, watching Gary's drill rig struggle. And he'd been watching for most of the morning with the expression of a man who's seen this before. Emmett was 78 years old. He farmed 140 acres on the ridge above the road cut. Cattle, tobacco, hay, the standard eastern Kentucky hill farm that barely pays and never quits. His family had been on this ridge since 1891, when his grandfather, Silas Boggs, had homesteaded the ground and built the first house from timber cut on the property and stone quarried from the same Berea sandstone that Gary's drill was now failing to penetrate. Silas had built that house by cutting stone from the hillside, not with a drill, not with dynamite, with a technique that he'd learned from his father, who'd learned it from the stonemasons who built the chimneys and foundations of Appalachian Kentucky in the early 1800s. A technique older than the state itself, used by men who had no machinery and no explosives, but who needed to move rock to build houses, lay foundations, and clear land for farming. The technique was called feather and wedge. Let me explain, because this is the engineering that Gary's $200,000 drill rig couldn't replicate, and that a man with a hammer and a set of hand tools could accomplish in a fraction of the time. Feather and wedge, also called plug and feather, or simply the wedge, is a method of splitting rock along its natural grain by applying controlled expansion force instead of compressive force. Instead of pushing against the rock's strength, which is what the drill does, you push between the rock's layers, exploiting the grain structure that every sedimentary rock has. The tools are simple. A handheld star drill, a steel chisel with a cross-shaped tip, is used to drill a line of holes across the rock face. The holes are spaced 8 to 12 inches apart, drilled 2 to 4 inches deep, and aligned along the direction you want the rock to split. Into each hole goes a set of feathers and wedges, 2 thin steel shims, the feathers, and a steel wedge that fits between them. The feathers sit in the hole against the rock walls. The wedge sits between the feathers. Then you tap the wedges. Not hit, tap. A light hammer blow on each wedge, moving down the line, 1 tap per wedge per pass. The wedges push the feathers apart. The feathers push against the hole walls. The force is lateral, expanding outward instead of pushing downward. And the lateral force follows the rock's grain, finding the natural planes of weakness where the sand grains are bonded, edge to edge, instead of face to face. After 4 to 6 passes of tapping, each pass applying perhaps 10 pounds of force per wedge, the rock splits, not shatters, splits, a clean fracture along the line of holes, following the grain of the sandstone, opening the rock like a book opening along its spine. The split surface is flat, clean, and predictable. The rock that a $200,000 drill couldn't push through yields to $30 worth of steel wedges and a 2-pound hammer, because the wedges aren't fighting the rock's strength, they're using the rock's grain. That's the secret that Silas Boggs understood in 1891, and that every Appalachian stonemason had understood for 2 centuries before him. You don't break rock by pushing harder. You break rock by pushing smarter, finding the grain, aligning with the structure, and letting the rock's own geometry do the work of separation. Emmett walked down the hill to Gary's drill rig at noon, after watching 4 hours of grinding with 11 inches of progress. Having trouble? Gary was wiping rock dust off his face. The drill bit was hot enough to steam when the water hit it. The noise had been constant, a high-pitched grinding scream that had been audible from Emmett's barn 400 yards away. The rock won't break. I've never hit Berea this hard. It's eating my bit and giving me nothing. That's the iron band, silica cement. My grandfather quarried stone from this same ledge in 1891. He said it was the hardest rock he ever worked, but he worked it. He had a drill rig. He had a star drill and a set of feathers and wedges. Same tools his father used. Same tools every stonemason in Carter County used for 100 years. Feathers and wedges on silica cemented sandstone. On this exact ledge, I can show you where he quarried. The tool marks are still in the rock. Drill holes, 6 inches apart, 2 inches deep. He split blocks 8 feet long and 3 feet thick from this hillside. The chimney on my house is made from stone that came from within 50 feet of where your drill is sitting. Gary looked at the drill rig. He looked at Emmett. He looked at the rock face that had absorbed 4 hours of drilling and yielded less than a foot. You're telling me your grandfather cut this rock with hand tools? I'm telling you, I can cut this rock with hand tools. I've got my grandfather's set in the barn. Star drill, 12 sets of feathers and wedges, a 2-pound hammer, and a 4-pound sledge. I've been splitting rock on this property since I was 16. The technique works on the iron band because it doesn't try to push through it. It splits along the grain. Your drill is fighting the rock's strength. The wedges use the rock's weakness. The rock's weakness? Every rock has a grain, a direction it wants to split. The iron band's grain runs northeast-southwest on this hillside, dipping about 12 degrees to the southeast. If you drill your holes along the grain line and put the wedges in, the rock splits like a loaf of bread, clean, flat. 2 to 3 minutes per split. Your 8-foot channel would take me about 3 hours. 3 hours. My drill has been running for 4, and I've got 11 inches. Your drill is pushing down. The rock is strong from the top. I push sideways. The rock is weak from the side. Same rock. Different direction. Different result. Everything was about to change. But Emmett had one thing. The $200,000 drill rig didn't. The knowledge of where rock wants to break. Let me tell you about the demonstration because Gary didn't just take Emmett's word for it. He watched. Emmett drove to his barn and came back with a canvas tool roll. Heavy, stained with decades of rock dust, the leather ties cracked and rewrapped with baling wire. He unrolled it on the tailgate of his truck. Inside, a star drill, a steel rod 18 inches long with a cross-shaped carbide tip. 12 sets of feathers and wedges, each set a pair of thin steel shims and a tapered steel wedge, the steel dark with use, a 2-pound ball-peen hammer, a 4-pound hand sledge, and a chalk line, a string in a chalk-filled case for marking straight lines on rock. Emmett walked to the rock face. He ran his hand along the surface, the same surface the drill had been grinding against for 4 hours. He found what he was looking for in 30 seconds. The grain. A faint linear pattern in the sandstone, visible only in raking light, where the sand grains were aligned in parallel layers. The grain ran northeast-southwest, just as he'd described. The bedding plane of the original sand deposit, compressed into stone 350 million years ago and still visible if you knew what to look for. He snapped a chalk line along the grain, 8 feet, the length of the needed channel. Then he picked up the star drill and the 2-pound hammer and began drilling holes. Not drilling the way Gary's rig drilled, not with downward force and rotation. Drilling the way stonemasons have drilled for centuries. Hold the star drill against the rock, strike it with the hammer, rotate it a quarter turn, strike again. The star drill's cross-shaped tip chipped a circular hole with each strike. The rotation cleared the chips and deepened the hole evenly. Each hole took about 2 minutes, 2 inches deep, 3/4 of an inch in diameter. Emmett drilled 12 holes along the 8-foot chalk line, spaced 8 inches apart. 24 minutes for 12 holes, then the feathers and wedges. Into each hole, Emmett placed a set, the 2 feathers flat against the hole walls, the wedge between them. Everything seated snug. He tapped each wedge once with the hammer, a light tap, seating it, not driving it. Then he went back to the first wedge and tapped it again, then the second, then the third, moving down the line. Tap, tap, tap. 10 pounds of force per tap. The sound was musical. The ring of steel on steel, repeated in rhythm, a 12-note sequence that Emmett's hands played from memory. On the third pass, the rock spoke, a sound like a rifle shot, a sharp crack that echoed off the hillside. A fracture line appeared in the rock face, running from the first hole to the last, following the chalk line, following the grain. The crack widened as Emmett continued tapping, a 1/4 inch, then 1/2 inch, then an inch. The rock was opening along its bedding plane, separating cleanly, the split surface flat and smooth. On the 5th pass, the block separated. 8 feet long, 3 feet wide, 18 inches thick. a slab of silica-cemented Berea sandstone weighing approximately 2,400 pounds. It separated from the hillside and tilted forward, held only by friction. Emmett tapped 2 more wedges at the base, and the slab slid free, landing flat on the ground at the base of the cut. Total time from first drill hole to separated block, 47 minutes. Gary had been standing behind Emmett the entire time. He hadn't spoken since Emmett started drilling the first hole. He was a professional. 22 years of drilling, hundreds of jobs, thousands of hours on the rig. He drilled through granite, through basalt, through the hardest rock the Appalachian Mountains could produce. And he'd just watched a 78-year-old man with a hammer and 12 sets of wedges do in 47 minutes what his $200,000 drill rig hadn't accomplished in 4 hours. 47 minutes, Gary said. About right for this grain. Looser grain splits faster. Tighter grain takes more passes. But the iron band on this hillside is consistent. The grain runs true for at least 100 feet in either direction. Every block will split the same way. I've been drilling for 4 hours and you split it in 47 minutes with a hammer. You've been fighting the rock. I'm using the rock. Your drill pushes down. That's the rock's strong direction. The sand grains are stacked on top of each other like a column of coins. You're pushing along the column. The column holds. My wedges push sideways. That's the rock's weak direction. The grains are bonded edge to edge in horizontal planes. The bond between planes is weaker than the bond within the plane. The wedges find the weak bond and split it. Same rock, different physics. They don't teach this in drilling school. They didn't teach it in school at all. My grandfather learned it from his father. His father learned it from the stonemasons who built the first houses in Carter County. The knowledge goes back to the 1700s, maybe further. Every man who built a chimney or a foundation in these hills knew how to read rock grain and split along it. The drill rig replaced the knowledge because the drill rig works on most rock without needing to know anything about grain. But when the drill meets rock that's tougher than it is, rock like the iron band, the knowledge is the only thing that works. That moment changed everything about the 3-day road job. And the crew that watched from the road would never forget the sound of 12 wedges splitting rock that a $200,000 machine couldn't scratch. Let me tell you about the rest of the job because Emmett didn't split one block, he split the entire channel. Gary hired Emmett on the spot. Not as a subcontractor with paperwork and insurance certificates, as a neighbor helping a neighbor, paid in cash, the way work gets done in eastern Kentucky when the official system can't handle the problem. Emmett agreed to $200 per day, less than Gary's drill rig cost per hour in fuel and wear. Emmett worked for 3 days. He split the 8-foot channel through the iron band, 4 courses of rock, each 18 to 20 inches thick, removed 1 slab at a time. He drilled the holes with the star drill. He set the feathers and wedges. He tapped the line. The rock split. Gary's crew lifted the separated slabs with the drill rig's boom. The rig that couldn't drill the rock was perfectly capable of lifting it once Emmett had separated it from the hillside. 3 days, 8 feet of channel through silica-cemented Berea sandstone. Total cost of Emmett's work, $600 in labor, plus approximately $20 in tool wear. Total cost of Gary's 4 hours of failed drilling, $1,800 in fuel, bit wear, and labor, with 11 inches of progress. The county road crew laid the culvert pipe on Friday. The road was paved the following week. The job was complete, 3 days behind the original schedule, but only because of the 4 hours lost to the drill's failure. If Emmett had been called first, the job would have been done on time. Dale Shepard, the county road supervisor, drove to the site to inspect the finished channel. He looked at the cut, the walls smooth and flat where Emmett had split along the grain, the drill marks visible where Gary's rig had ground against the surface without penetrating. 2 technologies, 2 results, visible side by side in the same rock face. The smooth walls are the handwork, Dale asked. Feather and wedge, Gary said, a 78-year-old farmer with a hammer and his grandfather's tools. And the rough section. That's where I spent $1,800 trying to push a drill through rock that doesn't push. Who's the farmer? Emmett Boggs, lives on the ridge above the cut. His grandfather quarried stone from this same ledge in 1891. The tool marks are still in the rock up the hill. Same technique, same tools, same result. Dale looked at the cut. He looked at the ridge. He looked at the smooth, split surfaces that Emmett's wedges had created. Flat, clean, predictable. The rock had yielded not to force, but to knowledge. The knowledge of where it wanted to break, carried through 4 generations of Appalachian stonemasons to a farmer on a ridge who still kept his grandfather's tools rolled in canvas in the barn. Let me tell you about the J.D. dealer because Travis Weaver enters this story the way every dealer enters, with opinions about productivity that don't account for what happens when productivity meets geology. Travis ran the equipment rental side of the J.D. dealership in Grayson, 20 miles north of the road cut. He rented drill rigs, excavators, and dozers to contractors across 3 counties. Gary's Atlas Copco rig was a competitor, but Travis had been watching the contract because the county was considering renting Travis's Caterpillar drill for similar work on 2 other culvert projects. When Travis heard that the Atlas Copco had failed on the iron band and that a farmer had completed the work with hand tools, he drove to the site to see for himself. He found the channel cut, 8 feet through solid rock, the walls showing the 2 methods side by side. He ran his hand along Emmett's split surface, smooth, flat, the grain visible in the exposed face. He looked at Gary's drilled section, rough, scored, the surface scarred by hours of grinding that produced noise and dust in 11 inches. A farmer did this with a hammer, Travis said. Feather and wedge, tools from the 1800s. He split the iron band in 3 days. I've been renting drill rigs to contractors for 15 years. I've never had a customer tell me they needed a farmer with a hammer instead of a $200,000 drill. Nobody needs a farmer with a hammer on normal rock. Normal rock. The drill wins every time. But the iron band isn't normal rock. It's tougher than the drill. The drill pushes, and the rock absorbs. The wedges split, and the rock yields. It's not about how much force you apply. It's about where you apply it. Travis looked at the tool marks on the hillside above. Silas Boggs's quarry marks from 1891, still visible in the rock 110 years later. Drill holes, 6 inches apart, the expansion cracks between them. The flat faces where blocks had been separated and carried downhill to build a house that was still standing on the ridge. Those marks are from 1891? Same technique, same tools, same rock. The method is at least 200 years old in these hills. maybe older. The stonemasons who built the first chimneys in Kentucky used feather and wedge to cut stone before the Revolution. The technique comes from European quarrying. The Romans used it. The Egyptians used it. Every civilization that built with stone developed some version of it, because every civilization that built with stone eventually hit rock that was tougher than their tools. And a $200,000 drill rig couldn't do what the Romans did. The drill rig can do things the Romans never imagined. It can punch through 1,000 feet of shale in a day. It can drill a well to the aquifer in 6 hours. But it can't read grain. It can't find the weak plane. It can't do what Emmett's hands do. Feel the rock, find the direction it wants to split, and put the wedge exactly where the rock has been waiting to be split for 350 million years. Let me tell you about what happened after the culvert job, because Emmett's demonstration created a demand that neither he nor the county had anticipated. Gary Hoskins told every contractor he knew about the feather and wedge method. Not as a replacement for drilling, Gary still used his rig on every job where the rock was drillable, but as a backup, a technique for the iron band encounters that every contractor in eastern Kentucky hit 2 or 3 times a year, the spots where the Berea Formation shifted from normal to silica cemented, and the drill rig went from progress to frustration. Within a year, Gary had bought his own set of feathers and wedges, 20 sets, professional grade, from a quarry supply company in Vermont that still manufactured the tools for dimensional stone quarries. He'd also hired Emmett as a consultant, $200 per day on call for any job where the drill hit the iron band. Emmett came out 4 times in 2002, 3 times in 2003, twice in 2004. Each time, he read the grain, drilled the holes, set the wedges, and split the rock in a fraction of the time the drill would have taken. More importantly, Emmett taught Gary how to read the grain himself. The 2 men spent a Saturday in the spring of 2002 walking the hillside behind Emmett's farm, studying the exposed Berea outcrops, learning to see the bedding planes, the grain direction, the subtle color differences that indicated silica cement versus calcite cement. Gary was a fast learner. He had the geological knowledge from his drilling career, and Emmett's visual method gave him a new way to apply it. "The grain isn't hidden," Emmett told Gary. "It's right on the surface. You just have to look at the rock the way a woodworker looks at a board. With the grain, not against it. Every rock has a direction it wants to split. Your job is to find that direction and agree with it. The rock cooperates when you go with the grain. The rock fights when you go against it. Your drill goes against it. My wedges go with it." By 2004, Gary had added feather and wedge work to his regular services, listed on his business card, quoted on his contracts, a $400 per day premium service for iron band encounters. He was the only drilling contractor in eastern Kentucky who offered the method, and the premium reflected the rarity of the skill. Other contractors called him when they hit the iron band. Gary split the rock and billed for the knowledge that a 78-year-old farmer had given him. Emmett retired from consulting in 2005 at 82. His hands still worked. The grip of a man who'd been swinging a hammer at rock since the Eisenhower administration. But his knees couldn't take the hillside work anymore, and the drive to job sites was wearing on him. He passed the tool roll to Gary, the same canvas roll that Silas Boggs had carried in 1891, with tools that had been resharpened 100 times but never replaced. "The tools are yours," Emmett told Gary. "The technique is yours. Teach someone else before you're too old to swing the hammer. The knowledge has been passing hand to hand for 200 years. Don't let it stop with you." Gary taught his son. His son teaches apprentices. The feather and wedge method that Silas Boggs used to build a chimney in 1891 is now a listed service on a modern drilling contractor's website. Priced at $400 per day, available anywhere in eastern Kentucky, where the iron band hides in the Berea sandstone and the $200,000 drill rigs grind to a halt. Let me tell you how this ends. Emmett Boggs died in 2008 at 85. His farm is still on the ridge, 140 acres, cattle and hay, run by his grandson, Dean. The house that Silas built in 1891 from stone, quarried with feather and wedge, is still standing. The chimney is original, Berea sandstone, split from the iron band, fitted without mortar, 117 years old, and plumbed to the inch. The quarry marks on the hillside are still visible, Silas's drill holes, 6 inches apart, the expansion cracks between them, the flat faces where the blocks were born, the Farmall 560 that Emmett used to haul stone from the hillside to the road is in Dean's barn. The canvas tool roll is with Gary Hoskins, who uses it on 2 or 3 jobs a year and tells the story of October 2001 to anyone who'll listen. The story of the drill rig that couldn't break the rock and the farmer who broke it with a hammer, and the knowledge of where rock wants to split. If this story stayed with you, subscribe to The Average Farmer for more. We'll see you in the next one. The drill rig pushed harder, the farmer worked smarter, and the rock, the same rock that had been sitting on that hillside for 350 million years, split for the man who asked it politely instead of the machine that tried to force it. Because every rock has a grain, every rock has a direction it wants to break. The drill doesn't know the direction. The drill doesn't need to. On most rock, brute force works. But on the rock that's tougher than the machine, the only thing that works is the knowledge of a man who's been reading stone since his grandfather put a hammer in his hand and said, "Listen to where it wants to split." $200,000 of hydraulic force, 11 inches in 4 hours, $30 of steel wedges, 8 feet in 47 minutes. The rock doesn't care about horsepower. The rock cares about where you hit it.